So, hello guys. All right, welcome, welcome. We're back in Hyperworks tools programming stuff, and today I have something quite tricky, I would say. Tricky because I don't really know how to tackle this one right now, and I have to figure that out as we go. But I think that's also making it a little bit interesting. So I'll start the hypermesh instance too, so that we can look at the model. And it will be a pretty big issue in terms of the Hyperworks tools. Um, I have a issue for it already. So determine the groups of slave nodes not based on a property value. So what exactly is that? Let's maybe back off a little bit and see what we are talking about anyway. Um, so basically, we started with a model like so, or something even more simpler, or simpler. This is a little bit more tricky because I now also introduced 1D elements, but that's another story. You can check that with the GitHub. But yeah, just assume something like this. Now, here I think it would be pretty easy. That's why this is maybe not the best model to show you. It would be pretty easy to separate groups of slave nodes for each RBE element. So if this is just strange words for you right now, let me explain. So an RBE element is something like this in this red here, this red element. This element couples the degrees of freedom on the slave nodes, which are the multiple nodes around it, and it couples them to one particular node, the master node in the middle. Now for here, it's not a problem to have separation between different components or properties for the slave nodes because all the ends of this spider, they just attach to the yellow part. The same is true also for this spider here. Every end of the spider attaches to a blue element. So there's no need for us to really distinguish between two separate components, right? But that's not always the case. So let's do something a little bit more tricky, something like this. This is, I think, also the model we had before. In this model, this spider, or this spider has slave nodes here and slave nodes there. And why do we even care? So basically, what the main target of this Hyperworks tools NPC or SPC forces, however we call it later, the main goal of this program is to give you a tool at hand which automatically does the following for every NPC in your model. It tries to it tries to give you an understanding of how much force is transferred over this particular NPC. And for that to be possible, we cannot do the following: take all the elements and sum up the forces we have. Because if we would do that, we would get a balanced force that would be 0, and this is not what's happening. So the balance is being one group of nodes pushing in one direction and one group of nodes pushing in the other, and those two are balanced. Otherwise, the master node would not be stable. And also maybe a little bit of a precaution here. This is all just valid for static analysis. Nothing transient, nothing time dependent and stuff like that. We don't care about this right now. We have no time dependent data. We have just one singular false value for a converged solution at the end, and that's what we're using. Okay, so you see we have the need for differentiating between two groups. The groups down there, the groups up here. Now how we do that? So it works, right? It works right now. And the way it works is that you would have different properties for elements down here and for elements up here. So you see the components, you have two components, and you have prop 1 and you have prop 2. And this is a requirement for my tool to work right now. And that sucks. Why? Because it just forces you to do something which is maybe not really necessary. It forces you to apply a modeling style which is complicated and unnecessary and even dangerous in some cases, because if you just think about something like which just has one component, I'm not sure if this would even work. I think not. So just think about not sure. Well, yeah, let me think of an example. So let's think about something like, let me get my pen. Let's think of something like you have an eye here and whatever structure here, and then you have a second eye here and whatever structure, right? And they are connected somehow. And then you have this blue spider, or green spider in this case, having a master node here. Here are one side, here's the other one. And you have, for example, maybe an SPC here. Or maybe a bar element here. So here you cannot really differentiate between the separate properties because you just have one. See, that's not really a good thing. Not sure if the method I have now in my head works for this too, and what should be done in this case. That's maybe a whole different topic. But for now, let's just tackle this one problem of how can we differentiate between those groups. Therefore, I created this issue, right? So this is the entry point. We have this issue, and we have created a branch for it, and now we have to fetch this. So let me do that. I do a little fetch, and then change the branch to be the origin 15. Determine the groups of nodes based on not based on a property value. The easiest model for this to work on would be the 2D model, and I think this would be the rigid FEM. Let's see if that still works, because I have not tested it for a while. So let's comment that out, and let's just comment in this one. So this should be the 2D model, and if I run that by simply entering task run here, which does the poetry stuff with the task file and stuff like that, we get an output thing here. And we have the property 1, we have the property 2, we have the forces here, the forces there. So that's all working good. Okay, so I think we can use this as a basis. Okay, now let's think what we actually would want to do, because there's separate ways of doing it. Basically, what I'm trying to accomplish here is having something like a by-attached functionality, but in code form. So you see, if I just select one element here, or let's do differently. The starting point is our element here. This element has different properties we could use. But the most important property is that I have a list of nodes. That means I know exactly the node IDs of all my slave nodes. I don't know how they are separated. I don't know this, but I know my slave nodes. Now, let's start with a slave node. Let's say this would be the slave node. So my goal would be to just have this group of slave nodes. I'm thinking of it. There might be even an easy solution for it, to be honest. But I'm not entirely sure if that's the case. This is the beauty of algorithmic thinking or algorithmic problems. You see a problem, you think about it, you just explain that problem to your colleague or so, and while you're doing that, you get suddenly an idea. Now, I will not lose the idea, but I will first present you my initial thought. The initial thought would be that I would want to have something like an attached. So let's start again with this node. So this would be a slave node, the first one we would have. The goal is to have all slave nodes, but just the ones connecting to the blue plate. Now, one thing how you could do that is it would be the common nodes between all the nodes of the blue collector and the nodes which are attached to these elements. Because if you do the common of it, those nodes don't count, right? Because they're connected to the RBE, but they don't appear in the list of nodes of the blue component. The problem is, to be honest, we don't have any idea about components. Components are not known to us if we want to do it really without the help of the properties or the component IDs. And that's what the goal is, to have it working without anything required from the user. Okay, let's start again. This is the node. So I can certainly go to the element, right, where this node is connected to. Maybe I get those two, to be honest. It's more than one. And now I could do something like a by attached. But be careful if I just now select by attached, it will select everything. Why? Because attached also means it is counting as attached if the MPC is working, right? But let's think again, if that would not be the case, if we would just simply delete this element and make the same thing again, select an element and say select attached. Now we just get all of the upper elements. And by just transferring from elements to node IDs, we would get what we want. Now, let's shuffle back. Now, this would be my initial idea, and now there's several different ways of doing this. The most stupid but working idea would be to start with a node, go to the element, go through every node, go through every element and see which element connects to this node, and then do this all over again until you don't find any change in the node list. So you're adding nodes and elements to lists until there's nothing more to add. Basically, you're growing. And this is some algorithms also used in different scenarios. But just imagine you're starting here, then you go and add a bunch of elements which are surrounded here. And then you do it again. So something like an advancing front. But this is also not really good. Why? Because it's very time consuming and takes a lot of computation power. Now, what's a maybe smarter solution to do it? One way would be to make use of neighboring relations. So if you're building your model and you figure out the neighbor relations and save that in an element file, so for example, I would say this element has as an information all the neighbors to it, right? It would be initially, or let's say it would be calculated once and saved in the element info what the neighbors are. And there's very great and efficient ways of doing this. Then you have this information, and it would not require you to loop through nodes and elements all the time, but you can just add neighbors until there's nothing more to add. But you have to be careful that you don't make a ping pong, right? From this thing you add this thing, and from this thing you add this thing, and so you're making ping pong, and it's nothing really what's there's no sense in that. The way of doing this efficiently would be using data structures which somewhat structure the elements like they are also structured here in the grid. Because the thing is, again, you could do the stupidest idea and just loop through the elements. I have to tell you that this is what I actually did as an initial solution in my PhD, and it was failing miserably. Let's think about it. How could you know that two elements are neighbors? Well, the obvious thing is that you just search for all the nodes, and then you search for all the elements which are connected to these nodes. So for example, this element has 4 nodes. Now you loop through all the elements and loop through all their nodes and see if any of those nodes are one of those 4 nodes. And this is really inefficient, because for every element you have to loop through every element. So that's not a good thing. The next best thing is to do, and I think that's also the strategy I went with then, because that works just so phenomenal, is to use grids. Or it's not really a grid, but it's more like a tree-like data structure where you place your element in, and the information where to place it on is given by the dimensions, or more or less the coordinates of the centroid. And that makes searching for neighbors so easy. And yeah, so the k-dimensional tree as a data structure, and sorting the elements into it by using the centroid. I think you need the centroid for it, or you need the geometric information. Yeah, and then you have this data structure, and then you can say you would like to find the next 1 to 20 neighbors. You still have to think a little bit about what the maximum neighbor count would be. So for example here, you could say, and initially be right, that you would have 1, 2, 3, 4, 5, 6, 7, 8 neighbors. But then maybe you are at a point like this, and then it's not true anymore. Maybe here it is true. Not sure. Yeah, but you find yourself pretty soon in a position where it's not true anymore. Might it be that it is mesh dependent? Might it be that this is because of a change in dimensionality? That could all be the case. So those are different possibilities of it failing. But I think you can then just make something like, what is really the biggest thing which you could encounter? So let's say you have 3 dimensions, so you would be surrounded by elements, and then you have dodecahedrons, whatever, something with really many faces, and then you just search for maybe the first 30 neighbors, right? It's never been more than 30. And then you have just those 30. And for those 30, you do then the test. You loop through all of them and see if one of the nodes are shared with the element you search the neighbors for. Excuse me. Right, so this could be a strategy to do it. Now, this was my initial thought. of doing it the same way I did with the PhD thing, right? Because that's so, it just makes sense. But right as I was explaining to you what we really want to do, um, is you can even get smaller here. Let's discuss that. So we start again with the node. We have one slave node here. And that first, let me change that. Yeah, you start with one node here. This is a slave node, and the goal is to get all the nodes around here. We cannot use geometry because that's unreliable as hell. So don't ever use geometry constraints. For example, give me all the nodes which are on this line. If you can say, or if you can detect the line there. So don't use geometry. But if you just think of it, you have this node. You can then go to the elements of this node. So that would be those two elements, right? And now the idea was those would have those elements. Those have nodes. And some of those nodes, for example the node here, those nodes are not connected to the RBE. Not at all. Some of them are. Okay, so you just filter out those nodes which are connected to it. Okay? Alright, let's do that. Then we would have 3 nodes all of a sudden. We had an initial node here, this one here, and this one here. All the others we can forget about because we just simply say we don't really know about those. Then you do the following. You're now selecting all the elements which are connected to those nodes. Right? And then you already can guess where I'm going. Now you switch back to the nodes. See which of those nodes would be connected to the RBE. Then go back to the elements. Oh, sorry. Now I messed it up. But now you would have something like this. And somewhat, on some point, you would have all the elements around. Can I make that by path? Wait a second. By path. So, what condition is met when you have all elements selected around it? I think the nodes, the list of nodes you have, which is a subset, and that's very important, which is a subset of the slave nodes, will not change. And I think this might be really a good thing. Now let's think about it. What would lead to failure? Certain conditions would lead to failure. And I would say simple conditions. That's why maybe it's not really the best option to do it like that. Although it seems to be very efficient and very smart from my perspective to do it like this because the computation is really great. It's not much. You just have to take couple of times the element and nodes side of things and switch between those two. That will just give you real fast results, right? So computation wise, it's not much. But okay, let's think about some condition which might break this. So let's say we have this element and then the connectivity would be broken at one point, right? Something like this. Maybe someone forgot to do this. Now you're still being able you're still being able to find all of the slave nodes here because you can reach this point from one side and from the other. So let's make it a little bit more complex. Let's just change it and let's have a disconnect here too. So let's start now with our model in mind. Let's start now with a slave node like here. Our method would work fine and would really go further here and here and here, but those nodes here will not get detected, I think. Why is that? Because there's no reason for this element to include this element at all. Because why is that the case? Because it has no node connected to the RBE. And this was the precondition for adding elements. So basically, it's not really a good strategy, although it sounded like a good one. And we even didn't think of 3D cases. 3D cases are a little bit more complex because then you have a third dimension where you also can have like missing nodes and stuff like that, and you also have to you have to grow in 2 dimensions simultaneously. So this makes it a little bit problematic to do it like this. Is there maybe another simple solution for it? I mean, I'm tempted to just implement something like this and see where it goes. But I think the other one would be to just implement a KD tree approach. So implement all the neighbor stuff and then having a method which just starting from one element then grows until there is nothing more to be found for 2D and 3D elements, which would be also not too bad to implement. And having a method like this could be also interesting for a bunch of other things. So yeah, I mean it's a bit tricky what to do here. My stomach feeling tells me that I should go to the known solution, the KD tree, because I think there's also some value in there to just put that out and put that into a Git repository to have that ready. So I'm tended to do this solution. The drawback would be that it is computation wise, it's a little bit more, yeah, it's a little bit more to do, and also to implement this is also a lot. Not a lot, but I mean it's more work. It's more work to implement it than just having a simple solution like this one I presented right now. Right. So, but I think we have to go with this solution. So let me explain the solution again. So you start with one element and then you add neighbors, so neighboring elements, until there's nothing more to add. And if you have then this subset of elements, which would be all the elements with one collector, because we skip MPC elements. We don't hop over to another component and add the elements down here if we started here, right? So we have then all those elements, and then you make a switch and say, what are all those nodes? And then you do the following: what is common in this list and in the list of the RBE slave nodes? And those are exactly the slave nodes which are connected to here. But for this to work, you have to have some prerequisites. You have to have the neighbor information. And you have this method of growing until you nothing more is there to eat, right? So this is more or less what I think I'll be doing the next couple of hours. I'm not sure how much of it I can implement today. Depends on how easy it is to implement the whole KD thing. Because I need to change something with the elements and stuff like that. By the way, I'm not sure if I covered that, but I did not sleep yesterday after the stream because I just wanted to get something more done here. But I didn't bother to turn on the stream again. And what I did was I have something like called entities. and then there's a node, there's an element, and there's an element 1D. And those have properties and stuff like we could use. And for now, we have a property ID, which we're using in the differentiation on the MPC, right? So this is being used right now for it. And basically, it's not that much of an interest in the 1D, but here in the element. I did not even differentiate between 2D and 3D elements. Maybe I don't have to. It could also be that we get away with it, because the structure or the data which we would like to do here, or the algorithms, would work the same on both 2D and 3D elements. All right, but we still have to do a little bit of thinking about it here. So basically, what's interesting to think about is the centroid calculation, right? But basically, now if I think about it, basically you could also maybe get away with it. If you just say the centroid calculation is like this, you calculate the mean of every node. So all nodes summed up together and the mean of it. So that's your centroid. It may be not correct for everything, but it's a pretty good assumption. And basically you need the centroid information just for the KD tree thing, so that you have the neighbor relationships in an efficient way. Yeah. All right, enough talk. I think now I will have to go to work and see if I can implement something like this. All right, let's do this. Now, when I create an element, I have a nodes list. So maybe we can do something like a centroid, which just is basically the position of the element. Yeah. So let's have something like this, centroid as a list. And now if I have the nodes, we could do something like self-centroid. Let's calculate the centroid. And that should be just the mean of it. So the centroid is 0, 0, 0 for node and self nodes. For I in rate 3, whatever, I sum up all the coordinates, and then I divide that by the length of the nodes. That seems right. Now we have something like this. Basically, the next thing would be to have something like neighbor elements. Self.neighbor neighbors. Yeah, neighbors and neighbor elements. It's very important that we don't mix the 1D elements and the elements here. But to be honest, that could also be a problem later on, because maybe we want to have just NPCs not in here. But actually, it is... Don't know about it. That's a problem for another day. So we have the self.neighbors. Then the calculate centroid function should definitely be just a private method. The calculate neighbors should be a public method, because the get neighbors is it has to be done when all the elements are created. So if you don't have all the elements there, there's nothing. It's nothing great of doing it like this. All right, now let's see what GitHub Copilot says about it here. So for element in all elements, if element ID is self.id. That doesn't make any sense. Well, it does not want to have the own element. Okay, so this is not a static method, but it should be a static method, I would say. And now let's see what it comes up with. Because that's not nonsense. I mean, you could, yeah, no. Well, let's think about it first. So it's not that stupid. So for element in all elements, so this would be its rather static thing. Then it says if the element ID is not the self ID, but I don't really know why the self should be a thing here. So this is kind of stupid. If self is neighbor element, then neighbors append. But the problem is this is neighbor. Let's see what the hell does it come up with. Yeah. You see, that's a stupid idea. What stupid. I mean, it's not stupid, but it is computationally it's really not good. You see, because you're looping here for all elements. But you have to do this for all elements, and then you have to loop for all elements again. Right? No, it doesn't do that. To be honest, I'm not getting what it is doing here. So let's say it calculates now for the element 1 if it is a neighbor of element 2. So the element, which is the element 2, element 1 would be the self, is getting into here. And now it just goes through all the all the nodes of the self and checks if they share a node. Yeah, basically, this is just the method of calculating the neighbors for one element, which is the self. And that's just stupid. No, that's stupid. So let's first do a static method. Calculate. No, get neighbors. It's correct to call it like this. Neighbors. Yeah, see again. No, no, no. That's all bullshit. Let's try, and because I cannot remember, to be honest, how to do this. But let's try to give him some information. Calculate the neighbors by making use of a KD tree. Yes. 3 dimensions using the centroid. What else? Get the 20 closest. And let's say, is 20 reasonable? If in a hex grid mesh, you would have 9 at the top, 9 at the bottom, and then you would have 8 in the middle. 9, 18, 26. Yeah, so let's maybe go for 30. Closest potential neighbors. And check if they're really neighbors by checking if they share nodes. Alright, so if you do that now in one go, I'm happy. I'm really happy. So let's import something. Does NumPy not have a KD tree? No, that's stupid. NumPy. Okay, well, let's first go with that, what we have here. So let's put the imports to the top. And you see now that we don't have something like this installed right now. So that means we have to add some dependencies. And yeah, that's overdue. So poetry add NumPy. and poetry add SciPy. All right. Now let's check that. Let's check that. So cards is a list of element centroid for element in element all elements. Okay, so this is a list of cards. Then we say we have the tree, which is a KD tree. There's nothing mentioned about the dimension here, but I think it will just get it from the cards. It's given as an input as a NumPy array. And now for element in all elements, the neighbors is tree query K30. Now I'm a bit confused because I cannot see the connection between tree and element. So here the neighbors should be a list of centroids. So for neighbor and neighbors, if the element is what? All elements neighbor. What does that mean? So element, if the element is To be honest, I'm a little bit confused about this. So the element centroid is like a three-dimensional vector. And this will get put into the KD tree, or not put into the KD tree, but queried from the KD tree. And what is queried is the K equals 30, the 30 nearest neighbors. But this should be then, because the KD tree is something which is centroids. So element.centroid, and centroid is also three-dimensional vector. I'm not getting that. So we have the KD tree, which is not the element, but it is more like a large list of three-dimensional vectors. And then it's sorted into the KD tree. Okay, so I can understand that. Then it gets the 30th nearest centroids. Yeah, that's a way to think of it. You get the neighbor centroids. And now for neighbor centroid in neighbors, 1. Oh, interesting. So neighbor is not really a centroid. What are you getting? What is this? Huh. You have to think about it. But let's say we go along with it. Now let's say if this is an element, if this is a neighbor, it's continuing on 2 occasions. I'm not sure what this is. So this seems to be like some error catching. And then if set element nodes intersection to element all elements neighbor nodes. So if the element and the neighbor share nodes, then element neighbors append the neighbor element, and vice versa. So there's definitely something wrong here, because it does not check if the neighbor is not already there. So I would say we can at least add that. All right, so maybe we can also get something. Check if the element is already in the neighbors. Does that make sense? No, that doesn't make any sense. Check if the element and the potential neighbor share nodes. Let's do also. I don't get this. To be honest, I don't get it. I don't get this. So this neighbor one is maybe yeah. Normally it's a location and also an instance which is put it into a KD tree. So if this is the case, and we now say for neighbor in neighbors 1. Yeah, so this is a potential neighbor. So let's make this a potential neighbor. Isn't it neighbors with just an O in American English? Not sure. Yeah, so potential neighbor seems to be an index. But why the... Why? Let's skip that. I want to see myself if this is really a problem. Now, this makes sense for me. The potential neighbor, that they have an intersection. So this makes sense. Ah, it's so ugly to read that, to be honest. Why does it do that? It's a line break. Does it have more than... Ah, okay, I think the formatter is broken. I'm not sure. Normally it should not reformat that, because yeah, I'm not sure, but normally the line break would happen after 100, but I think the formatter is set to be breaking at 80. Seems to me like that, because that was concerning a break, and yeah. Yeah, you can argue about what's more readable. Okay, now, yeah, let's say that works, and now we would have a neighbor definition. I still am 100% sure that it will not work for right now, but let's see. So basically, we have to see where we create the elements. So let's see that. We search for element. So no models reader, right? So build nodes to property. Yeah, maybe this is all not necessary anymore if we have something what I'm intending to use right now, but for testing purposes, I would say it's okay to just do that. Yeah, speaking of testing, we should have something like a playground where we can test things out. So let's make something like a playground neighbors. And it bothers me that I did forget how to write it. Yeah, I think that's American English, right? Yeah, maybe we'll leave it like that. But maybe it will be mixed in the code because of the GitHub Copilot, but yeah, that's okay. So, let's go. We have our playground neighbors. Why isn't that here? Should be here. Now I will copy from here. I will copy all of it. Now, block size, whatever, that's all okay. I would say the input folder, that makes also sense. Then, now let's see. The NPC force extractor get NPC forces block size. I don't think we need that. Is it? Ah, this is the main class. Okay, we need that. Yep, 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 yep. So basically, after that, we can play around. So we can delete all this. After here, we can play around. Let's maybe do that rather here, without any class. Yeah, let me quickly get that ready. Yeah, and I think that's about it. Nobody needs that, right? So the block size should be there. Okay, we don't need that. I think that's it, right? So we can delete all that. We don't have that and that, and we don't have that. Okay. All right, so I would say we change it temporarily that we are able to execute this. We change the VS Code settings and we now change this to playground neighbors. So if I press F5, this should then execute this thing. Cannot imagine that this will work. But yeah, okay, let's see. So the build node property would work then. But we did not even do something like the print neighbors. So, but this is a playground, right? So I'm testing code here now and see what it will get us. Okay. So let's just print the elements. Yeah, for element in reader.elements3d. Is this a thing? Does this have an elements 3D? It's not a bad idea, to be honest, to do this. Yeah, it is something here. Yeah, nice. Is it also being used? Yeah. Yeah, okay, good. Yeah, let's try that. Yeah, there's nothing here, huh? Ah, oh, okay. It also says it has no module named Playground Neighbors. Huh. Playground GH neighbors. Yeah, once more. Okay, now I have an error. String object has no attribute cards. Yes, I mean, that is correct. Why the hell would nodes be a list of integers? A list of strings. Haha. Okay, so there's a problem here. When I'm creating the nodes, the element 3D, when I'm creating the element 3D, I append whatever here, and then we have nodes here. And this nodes is just a simple, haha, okay. That's not great because I don't have information about the grid points. Yeah, but there is a, so we have to change all that. Oh, this will break everything. Yeah. But yeah, okay. 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 We have the read nodes method. The read nodes method does the self node ID to node. Yeah. Okay, so we have that. Then that means when I do my element thing, the nodes. So this is the node. Why the hell does this not use the nodes? Huh? I'm not sure. Ah, okay. No, this is correct. This is correct. This is correct. But yeah, so node IDs. That's node IDs. So what we should do here, nodes, is self node ID to node, the integer node ID for node ID. Yes, exactly. So this is the same thing for here, but not here. Ooh, I think there's a bug. There is a bug. This should happen after this one. Because if there's a second line, node IDs has to be extended, right? So node IDs has to be extended. That's not happening for 1D elements, but it's for sure happening for 3D elements. Okay, so then for node in nodes, so this will fail. Then maybe that we don't break our complete code right now. Let's change that to node IDs. Okay, then let's run it again. Let's see what it comes up with. Certainly not another error. Cannot access local verbal node IDs. Why? Ah, nodes IDs. I would say node IDs makes more sense, right? Okay, I think we have something. So basically, we have now just confirmed that our centroid method is working. That's a great thing, but nothing with our neighbor calculation. Where's the playground? Here. All right, so now comes the tricky question. I want to print the neighbors, but before I can do that, yes. All right, let's import the element. This will be funny. Most certainly it will fail. No? Okay. It's for sure it's not the correct the neighbors for print. No, let's do. Yes, let's do something like this. Element ID, element centroid, element neighbors. Now the element neighbors is not a good thing to print, as I saw. For no, for neighbor. We don't really want the neighbor centroid. But that's okay. So I think we can work with that, and that we don't get completely overloaded. Let's introduce a counter, and let's for every element plus equals 1, and if counter is equal to more than 10, then we will break. I would say that's reasonable. Let's see if we can get something which is somewhat reasonable. Okay, so first of all, I really hate it. Duplicates are not a good thing. Isn't there a data structure in Python also which is corresponding to the hash set? Something like a hash set in Python. A hash table. Well, we have a set, right? But I don't like it. I don't like it. Basically, we should understand why the hell does it do duplicates. So you saw I just asked if the element is not in element all elements potential neighbor neighbors. If it's not in the neighbor, then I put it in there. And if the other way around, same thing. Ah, this does not make any sense. Can we just leave that away? Tricky question. So I'm starting at a certain element. Then I'm looking through the 30. Yeah. So what I can definitely say is that this is efficiently not optimal. But let's think about this again. So I start at a particular element, and this element now is inputted into a KD tree with all the other elements too. Then you get the 30th neighbors, which could be neighbors, and I can already tell this is just no, I cannot tell this is bullshit. But so you get the 30 potential neighbors, and if there is some shared nodes between this and the element, then I would add it to it. And because I'm so inefficient on the computational side, I do that for every other element too. Because normally I would have to check something off, right? So I would say, all right, I have flagged the element. I did that. I did the check of for the elements here. But I cannot really check off the other neighbor element as well, right? Cannot do that. Cannot. But let's try this again. Without doing the vice versa stuff. That maybe seems stupid. So this seems more like it. Okay, and we have some self IDs. Yeah, so the self ID is stupid. The potential neighbors. Continue to avoid self as neighbor. Correct. If element ID is the potential neighbor ID. To be honest, this drives me nuts. So let's do that differently. No, that's not correct. This should be something like this. This is the potential neighbor, right? This is an element. And so we could replace something like this with that. Yeah, so that we have less of a syntax cluster. Man, yeah. Oh, it's so much more readable if you don't have something like that. Okay, the index should be here. That's more like it. Let's run that again. But it seems to be not that bad. So from first sight. Okay. Hmm. 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 Let's see. So this is the model we're using. I think this should be the one we have opened right now. Which one is it? Simple rigid. Oh, no. Simple RBE free. Okay, let's run it again. Okay, let's look at the 7055. So element by ID. Can you see it? I cannot see it. This one. There should be an option to put IDs on. Can I search for that? Ah, yeah, display IDs on off. Is it this one? Huh, no. Well, we can look at here, so that's not a problem. All right, so let's see. We should have 1, 2, 3, 4, 5, 6, 7 neighbors. 1, 2, 3, 4, 5, 6, 7 neighbors. That seems good. Now, let's see if the first one is in there. Huh? Can I not see that? 76.5. 76.5. No. Yes. Yes, I have it. Okay. 7013. It's there. 1805. It's there. 7. Huh? What? Huh? Okay. 1664 is there. 1724 is there. 1791 is there. 1856 is there. And 1805, I think I checked that already. It's there. Yes. Nice. Nice. That's great. That's not bad. That's not bad at all. So we have now a method which has the neighbors. That's not bad. Now, now it will be a funny new method to do. I would say this basically is a good description because we did it ourselves. Take some bright new element decorators and descriptors. So now let's do something like get all connected elements. Self and then element. Is this a static method? Oh, basically, yes, correct. I think there should not be a static method, right? Right. Not sure. Because we can do that for one element, right? So that could be just an instance method. Okay, let's back off for a quick second and recap what we did. Now we have now neighbor information, but that doesn't serve us well if we want to try to get all the elements of one component by just looking at one element and then adding all the neighbors. So this is what we are doing right now. So we trying to get a method which starts with an element, which is in this case the instance of the element itself, because this is a method which belongs to the class element. At least it should be, yes. So it's get all connected elements. It starts from the elements. Now, connected elements is a list. an empty list at beginning. Then for neighbor and self neighbors, connected elements append neighbor. So all neighbors will get added. That's fine. And then connected elements plus equals self get all connected elements for neighbor. What? Yeah, this is not valid anymore because we had changed it. Let's GitHub figure it out once more. Yes. Well, the problem is just that we would not want to have something like a ping pong effect. All right. So we have to continue if the neighbor is already in connected elements. If neighbor not in connected elements. Yes. Is that correct? I'm a little bit careful when it goes to how is it called? I'm forgetting the name. So basically you're calling your method on your own. And this is recursive programming. Yeah, recursive function calling. Yeah, so this is happening here. And I'm a little bit refraining from doing something like, okay. So let's see. So if the neighbor is not in connected elements, that means I have never seen that element before. If I have seen it before, I also have the reverse, the recursive thing happening here. And also, what also could be the case is that I have something like an overflow with the maximum depth being reached. So we have to account for this one too. So be careful with recursive stuff. It's not too hard to understand it, but the depth could be pretty soon reached. But let's think about it. How is it? You go through each neighbor, but then again for each neighbor. I think. Well, for our simple models right now, this will work fine. For our simple, yeah, this will work fine, I think. But maybe we will have to change that later on to not use recursive style. So, but then you have the connected elements, and maybe we would like to have another method with get all connected nodes. Because that's what we're really looking at. So okay, so connected nodes is nothing. So for neighbor in self neighbors, for node in nodes, if node not in connected nodes append, return connected nodes. Yeah, that's not really it. Let's say we would like to do something like connected elements. And now for every element in a connected element, for node in element nodes, if the node is not in connected nodes, then connected nodes append this and then return the connected nodes. Correct. So, and let's do a little bit more of a type hints. So this gives back a list. This should also give back a list. Okay. Yes. I mean, that's not bad. It's not bad. If that works, this is really not bad. Now how should we? Yeah. Well, still missing something. If we think about it again from the beginning, so we start at an RBE3 element. The RBE3 element does not have any idea about the elements. It just has an idea about the nodes. So I would go through one node and then have the element which is connected to it. And maybe it's not such a good thing to iterate through all elements every time you have an RBE. if you would not like to do this, you would have to have something like a node to connected elements, right? Yeah. You would have to do that. It's not too bad to have that, but I think it will also require us to restructure our code again. So let's just think about the entity node. This entity node has nothing. This has no idea about the connected elements. Yeah. So let's say we have connected elements is a list. And we would also define a method. That's not bad, but we don't. Yes, we want to do that. But that's maybe later. Later. I think this is not good right now. So we want to have something like a def add element. Yeah. And here it's important that we check that if the element is not already in there, then we can have an add that. Because now, for example, if you create now this 3D element or 2D element, we have this nodes, right? And this nodes is a list of nodes. Hopefully. Yes, I think so. We changed that today. And if that's the case, we can now do for node in nodes, node add element self. So we are adding the element to the node. And that means I can then later in the node instance, I can easily get the element connected to it. So def get all connected elements. Let's see how this is going then. So connected elements is an empty list for element and self-connected elements. Do I have that? Yes. Connect element if element not in connected elements. Huh? That's stupid. Is it stupid? Yeah, it's all stupid. So we can have the connected elements as a variable. It's public, right? So we can access that. I would think about much more about private and public and getter setter stuff at Java, but it's just not necessary here in this thing. Okay, so node has disconnected elements. All right. So basically now I think we have all the tools necessary to really do some damage. By damage I mean to get rid of all the property ID stuff what we have been thinking about at the beginning. And why that? Because now I think we can now cover the full routine. We can now go to the node, get the connected elements, get one of it. Yeah, one of it is enough. Then make our growing whatever, getting all the elements, getting all the nodes, make the intersection between that and the RBE slave nodes, and then take away all those slave nodes from the RBE. That means that we don't really consider it anymore, and then do the same thing on the other side as well, because the first approach will just blow away all the nodes up here, because those are then done, right? Yeah, and then we do the same thing for the blue component as well, and this makes it a lot easier. But I have to test that. And do we have now the RBE elements already? I'm not sure. So let's see about the methods here. So there's the read lines, read nodes, because there is this get rigid elements, right? And we don't have that right now. So let's do that. Let's do that. So in the playground, let's get the rigid elements. So I think we can strip away all this. We don't need that anymore. So the neighbors is being done here. Let's also do that for a moment. And how can I now, for rigid element, in reader.rigid elements, let's see what the printing stuff is. So print the element nodes. No, come on. What do we have here? The property to nodes. Interesting. Yeah, we can change that here completely. So the rigid elements is a list of MPC, and the list of MPC has then, it has the master node, but it has nodes, right? So this should be it. It's a list, but actually I think this should be something which is not, it's not a node instance right now. This is, I'm pretty sure it's still, where would that be? That would be here. That would be here. So it's still something which is an integer, right? Yeah. Yeah, and that brings us to the conclusion that we would like to change that completely. So node IDs is now an empty list. We have a node here, so that should be node IDs then, and that should be node IDs. Can't wait for the linting. God, the linting will kill us today. Now we do all that, and that should be the nodes, node IDs being appended, and yes. So then again, node IDs. And now, dear friends, this now is a self.node to nodes ID. Ha ha ha. That's a list, right? Something like this. Yes, now the nodes are proper instances. And now the NPC is now nodes list. Yes, and that property to nodes, I would say you can throw that out of the window. And sort nodes by property, you can throw that out of the window. And sum forces by property. That's exactly now what we are dealing with. But I think still it's not, maybe not the best idea to just delete it before even testing it, right? So let's keep it for now. But let's do the sum forces differently now. So def sum forces by connected parts. There should be a node to forces dict. Yeah, same thing. Yeah. Let's see what this comes up with. No. Basically, that's complete bullshit. So first of all, we have to do the splitting of the parts. And that means that we would have to do yeah. Let me think for a second. We would, first of all, we would have to get the slave nodes. All of them. Then we start with the first slave node and do our shenanigans with the element functions. This will take away then a couple of slave nodes. So this is the first thing. So slave nodes. What should that be? So that should be a dictionary. So part ID. Yeah, how should I call that, to be honest? Because I cannot even guarantee that it would be the same component. that that comes really difficult real fast. But let's just do part ID to slave nodes is a dictionary. Now for node in slave nodes, the part ID is the node.part ID. No, that can no. For node in self.nodes is also wrong. I would start with should that be a while loop? I think so. Oh, okay. What is this while loop? This while loop would be while the nodes in the dictionary, while they are not completely covering all the nodes in the self.nodes. Wow, that's complicated. Maybe I have to do that differently. Maybe I have to do that differently, because why do I do it here? We have those beautiful element methods right now, but we don't really use them. But to be honest, we have to start at the node, at the nodes of the RBE element. What comes to my mind is a stack. A stack would be something where I can take away from it. Node stack. Let's see if that works. Right now it's not really helpful. So the node, this is the first node I will pop here. Then get one element. I only need one element. So element is node connected element. Yeah. So this would be a connected element 0. There cannot ever be a case where I have, hopefully, can there be a case where I have just 0 connected elements to a node? Could there be a slave node attached to a SPC? Wow, corner case. I don't deal with it. So I have the element. Then, yeah, yes, yes. Hmm. The part ID to nodes. This is the maybe it's also better to do node IDs. Yeah. And then I think it's the same stuff as here. It should be then the same stuff as here. I still cannot believe that it would be something like that it would really work. So this is correct to happen after that. Then I think this all should be here. Yeah. Hmm. Something like this. So this should be that. This should be it. Yeah, still I cannot believe that this will work. Let's see if the while loop is correct, because that's at forces for each part. Yeah, so basically what this is doing, get the connected nodes for each part. That means attached elements. Yeah, I'm doing that. So the connected nodes. Yeah, but this is wrong. Um, part nodes. Hmm. Uh, how did we do that with the intersection? Was it with the entities? Yeah, set and then intersection and then another set. Okay. So okay, I think we can do that here as well. Where is it? Not here. It's with rigits. So set of connected nodes. Those are entity nodes, yeah? So those are not integers. Then intersection, if that's even possible. I think that's not even possible, because how should it be able to do an intersection not based on something like an integer? Integer is clear, but an intersection of instances, does it work? I'm not sure. So those are the part nodes. Then we would say node stack, not append, but pop all. those nodes. Then node ID for node in part nodes. Yeah, so let's basically walk through it again. So we have the connected nodes. So those are all node instances of the elements which are connected to this first element. All right, then the part nodes is the intersection between that and the slave nodes of the RBE, that we don't have anything different. Then we pop all the slave nodes, so that the found part nodes. Then we put that here into here, then we increase the part ID. Yeah, it seems not bad, but hmm. Yeah. Let's see if this works. Oh man, let's see if that works. That will definitely crash. I would not believe it if it would work. Or even worse, we have something like a runtime exception. Invalid literal for integer of the base 10. Uh-huh. Far before that. Okay, so the master node ID. Huh? So the line content would be that 0, 1, 2 is nothing. I think that's false, right? This is a bug. It should be the 3. Yeah, this is a bug. Ah, this doesn't work, yeah. This is a bug. So I did not test RBE3, but runtime, speaking about runtime, this is awful. So the runtime is really bad. Okay, cannot access local variable nodes where it is not associated. Yeah, I think because node IDs, I think there's something like, there's, yeah. Okay, again. This what's taking so long is the neighbor calculation. So maybe we have to do performance issues. Okay, here. Node IDs to node. And then we have the key of, is this a string literal? For ID and node IDs. Yeah, that's the problem. Can we maybe have an integer here? So the testing was awful too, because those are all bugs which should surface long before. Okay, now we have something which is more interesting. MPC sum forces by connected parts missing one required positional argument. Yeah, let's quickly look at what this was. Node to forces. So I would have to do something like this. MPC forces reader. But this is this in here too? Yeah, no, it's not. Okay, so I can use this and go back to the playground and say I have something like this, and there's then something like this. And then we are all good, but we're missing the MPC forces reader as something here. Okay, we don't need the element anymore. So node to forces. There's some problem here. No, it's not that. But the self Yeah, the MPC file path is missing. Yeah, so should do that. MPC file path. Yeah. Forces? Why the hell does it not? Yeah, okay. Yeah. So like this. Run it again. There's some awkward printing going on. Maybe should do not do that. Okay, now list object has no attribute connected elements. Node stack. What the hell is this? Okay, so self.nodes. So this is an object. And then pop. What is node then? Still a list? Huh? Okay. Maybe we don't have to do this. Is there... I don't have a clue about stacks in Python, so I will just Google that quickly. Like we could also use a list for it, right? Won't this work? So self nodes should be a list of instances, right? Yeah, I hope so. Because that pop here should remove one node, hopefully. Set object cannot be interpreted as integer. What? I would understand it if it's the problem. Okay. So what we would need is a method like a pop all. Um, Something like this. It takes quite a while, so performance-wise, this is not a good solution. Not at all. But it's somehow finished. Okay. No way. Come on, no way. No way, not at all, because we don't even write out something like that. Yeah. Well, it finished successfully. There's something which is returning, right? So it returns the forces. So we could do something like a print that thing and do it once more and see about that. There's a lot of performance to be gained from different areas, I think. Okay, this is not good. This is not good at all. Okay, it seems that we have found 92 parts. 92 parts. That comes dangerously close to the number of slave nodes, I think. So this is not working at all. Okay, maybe we have to see about this. Well, at least it removes some of the nodes and stuff like that. That's a good thing. But I think this intersection maybe is the problem. I'm not sure that this is working. but we will see. Now, let's go over it. So we have a node here. So the node would be the 10388 at this location. Then I would like to have the element. Element is 497. Now comes the big part. Gather connected nodes. Length is 0. No. Why? Why? Why the hell is this not working? Okay. So I know I have to step in here and see why this is not working. Takes a lot longer, right? Compared to before. Okay, I step now into this method. Now the connected elements is get all connected elements of the self. What is self? Self is an element ID 497 and it has no neighbors. What can it be? 497 has no neighbors. Which is the 497? If it's if it's now this element, no, that would be too easy. So let's see, element by ID 497. And we play the blind Manu again. Here. So that's bullshit that it's not having any neighbors. But for sure this then cannot work. But why? Did we get rid of the... Oh, okay. Yes, we did get rid of that. But wait a minute. Wait a minute. If we did not even do the building neighbor thing right now, what did take us so long? That's interesting. So something is... What? Not NPC. What did take us so long? Okay, let's do it once more. And I still would like to do and check for this. Now, if it now takes even longer than before, then it's definitely our neighbor method. But it seems to me that it is not that much of a problem. So, but let's jump into it. So jump in here, then the connected elements is... Oh, I think I clicked the wrong button. Oh no, I think this method can take a while. This is perfectly fine. That this takes a few seconds, maybe a little bit more. Because this is now doing this all growing thing and stuff like that. And we even have no idea if it does not contain some infinity loops in there. Could be. I have not checked that. And also because of the recursion def. Oh, I have no good feeling about this. Yeah, I have absolutely not a good feeling about this. Right now, I think we are caught in an infinity loop. Because of those ping pong games, I think the code is not playing with us. So basically, I blame this method for being incorrect. Connected elements. Well, I try to see that it is... if it's not in there... What could we do? Um, so what could we do? The neighbor should not reference back to it again. Yeah, you know what? For neighbor instead of neighbors, we just print the connected nodes, connected elements, and just run it again. It don't really bother of debugging. I just would like to see what the length or what the evolution of the connected elements would look like. An empty list? See, it's growing. It's not growing. An empty list? Yeah. Yeah, for sure. That is a problem. Recursive functions 101. We called the method again, and then we just simply reinitialized it as an empty array. Yeah, that is not a really smart strategy. Let's kick that. I don't like this at all. So let's do something like a while. The length. Yeah, this is also not good programming. But let's just make an infinite while loop. And now for eternity, length before. Yeah, something like this. Because I don't trust it. Let's see what the list evolution looks like now. Yeah, I want to see, to be honest, I want to see that. Let's step into here. Let's see. So it's an empty list at the beginning. Are we getting all the neighbors? Well, we have a bunch of them, right? So we're going again and again, all the neighbors. Oh, that's all? Okay, so it's better, but it still has the same problem. Okay, we are a bit better, but not really. So let's do it again. The basic what I want to understand is why this is not working. And I still think or still blaming the intersection method that this is not working. So the element we got picked is 497 and the connected nodes is now the interesting part. Connected nodes. There's 13 connected nodes. That seems an awful less. So this is not really great. There should be a lot more nodes. So let's see. So get all connected nodes self. It gets all the connected elements. I think here's a problem. So at the beginning, the element to check is the self. Then we have the element to check neighbors. We doing all that. But now we have to add. Oh man, that is ah. Oh, I can see. I can always. I can almost feel the computational requirement to do this. And if I do it stupidly, then it will be insane. Haha, then returns all connected element to the given element. So let's just make something like this. And let's just do it again. For element in self and connected elements. Now for every neighbor here, if the neighbor is not in there, append it. um, yeah, that's... Ah, this is all bullshit. But I think, so my feeling is that I have to give in a list. I have to give in a list which contains all the elements I have until this point, and it will then be added in the future. Yeah. Let's see, length before is the length of connected elements. And then if... Then we have somewhere we have a length after, and if I will return that. Now the question is what is happening here? So add all the neighbors to the connected elements. Well, basically, first of all, if length of connected elements is 0, I will add the self. Okay. Now I can loop through all of the neighbors. And no, loop through all of the connected elements. And add all the neighbors to the connected elements. So if neighbor is not there, then we add this, we append it, right? And then we check the length after, and then the connected elements is getting measured again. And if the length before and after, if those two match, that means those have the same length, nothing new has been added, I can return it. If that's not the case, else return self get all connected elements of the new connected elements. Now the self has no meaning, to be honest. And I don't really like this, but I think it has a fair shot. It has a fair shot to doing what we would like this method to do. But it will take a lot more. Paw. And I'm still scared about the recursive def, to be honest. Because it's not infinite. So let's just continue doing it, and then we have a problem here. Element get all connected elements missing one Yes. Um, yes, this is a problem. We can do an empty list here, right? Because I really would like not to set it. And in the recursive function calls, it's getting set automatically. And I think then I don't need to worry about it this much. Hopefully no infinite loops. Connected nodes. No. It has something? Ooh, 19,600. If that's all the elements, yes, yes. No, come on. Come on. Come on. Why is it all the elements? Why is it all the elements? No, I think I'm misjudging that, right? No? No, I misjudged. No, I think I'm correct. So it has still a problem. I'm not sure why, but yeah, let's just continue doing it, and I think we will get one. We will get one part back. But basically, why did it return to the connected nodes equal something? Because if I have all the elements and all the part nodes, then I think yes. So still a bug. And this bug is still, I think, the intersection thing. But let's see if the part, if the node, if the part nodes intersection, if that works. Because roughly, I think we have something like, how many slave nodes? We have 90 slave nodes, so it should roughly get us, oh, infinite loop? Infinite loop. Okay, why is this a 0? Wait a second. Node connected elements. Yeah, so there's something missing here. Yeah, let's quickly check the first bug first. So I think testing will not have a place for today. Because yeah, it's getting late. Okay, so the element is node connected elements and then 0. And connected elements is all the elements. But this connected elements, where is this even being calculated? It's for node connected elements. So something is wrong here. Something is wrong here. Node connected elements. Why? So let's see. Node is number 10,388. And then this node has connected elements. Many. All. So this is a first bug, but this is not the one we are currently dealing with. So does the connected nodes, is the element it's an arbitrary element. Not sure why this is working. But yeah, this is working because I have an index of 0. Then you get the connected nodes, and how many nodes are there? 8,600. So is this all the nodes there is? Or is it less? So that's 20,000. Yeah, so 8,000 is less, right? Would be funny after all. It's not matching anything, but yeah, so we have connected nodes here. And this is 8,600, whatever. Now the part nodes, this is not an important thing. What will this be? This will be an empty thing. Length is 45. Hey, it's half of it. That's not bad. So the node stack has 91. And now let's continue until here. What's the node stack now? That's 46. Okay, let's do one more loop. Ah, maybe because... Yeah, okay, I see the problem now, I think. The node stack will not get removed. Ah, what is it? So the node stack still has the 46 nodes in it. I would just do one more try and see if it's not decreasing. Oh, length is 2 now. What? Sorry. Node stack. 45. Let's do another one. Hey, it decreases it by 1 node. That doesn't seem right, does it? So we have a new node, right? So this would be 10.3.8.5. Then we would get the element, which is it connected to. 497. So now I think I know where to look. This should be somewhere near here or here, but it isn't. Yeah, but that's the problem. That's the problem. We get just a random node. And it just happens to us that it would always get on the one side, but then the intersection then is 0, and then it will not get more removed than 1. Okay, that makes sense. Okay, now, okay, I think I have pinned down the problem. So disconnected elements by node is just rubbish. So this add element, this add element, where is this called? It should be called whenever I do something like creating an element. So I would say this would be called... No, wait a second. This add element. Something for node and nodes. So the result of this is obviously that we would have like all the elements for all the nodes. Something is not adding up. So add element. If element not in self-connected elements, then self-connected elements append element. This seems to be, for me, that seems to be correct. Something here is fishy. Something here is fishy. Why doesn't it do anything? Okay. So those are 3 nodes. This is a trier element, I think. And then we have this add nodes. Yeah, ba. Now, we would have something like a... What's it called? We would have something like a node dot connected elements. Maybe the redefinition is the problem. So if I have the nodes here, we'll quick get to one node and say the connected elements. Connected elements should have length 1. Why is it length 1? Should be more than 1. Yeah, something like 3. Always 3. Yeah, so, this seems right to me. But then again, if I'm looking here, and if I'm looking then node connected elements, right? Why should it be that all the elements are being added to this particular node? So let's skip that for now. I think this is correct. Maybe if I'm doing the linting, I'm almost certain that there will be something like a redefinition thing which happens. So node is node stack pop. So let's go to the first node. Then we have all nodes, yeah, but then you have connected elements, and this I don't get. Where the hell is there are? Is it possible that we have something like? So it must happen before the sum forces by connected parts, right? So this is what we know. So it must happen maybe here. No. That doesn't make anything. So then it must maybe happen here. No, there's nothing here. And the MPC thing here. There's the connected nodes. Yeah, but this is where it's already too late. That's already too late. Okay, so it cannot happen there. It cannot happen here. Cannot happen there. You know what? We have to check that. Maybe it's in the element get neighbors. Maybe it's the problem here. But I don't think so, to be honest. I don't think so. Let's see. We do the following. We start at the beginning and check our nodes if we have something like that. Is there something like global variables? There's nothing here. So there shouldn't be anything here. And the build node to property, is that maybe a problem? Node IDs to node. Let's see for one node, for example. The connected elements is not there. So before I even begin to think about the elements connected to the nodes, it's not being done here. So let's continue. The reader build node to property. This is exactly where we have. Yeah, now let's see. Is it now that it's already too late? Yes, yes. Okay, so here is the problem. Somewhere here's the problem. The line content, whatever. Then we have the node IDs. If we have something like that, it's that. If we have that, it's that. Node IDs, nodes. So in the element creation method, it cannot be the problem. But somewhere it must be. So if I do this element, is it maybe that I'm missing something real trivial? I'm almost sure. So the connected element. Yes, I think this is it. This is it. This is almost certainly it. So let's see. Reader has some elements and the element has some nodes. Yeah, nodes. So the node has connected elements, hopefully. Yeah, okay. Man, what a joke. Okay, this was a problem. Okay, now I would say I can quickly run the code completely through and see if it does something, which I think. Yeah, what could we do here? We could print the length of the stack. So what should happen is the length of the stack is at the beginning like 90 something, 92. I'm not sure why 92. Normally I would say 90. But that could be because we changed the modeler slightly. Yeah, we removed 2 nodes. Yeah, so 92 is fine. So 92 would be the node length of the node stack. Then let's just loop here. Let's just loop once. What's not a node load stack? Is 72. That doesn't make any sense. But let's continue. Then the length of the node stack is 71. God damn it. I don't know what the problem here is, but I think there's something like um hmm. Okay. This is a bug. Interestingly, this never happened to be a problem. Okay, let's run it again. So it takes an awful lot of time. That's the first problem I have with the code. Then it still is not correct of doing it. So normally what I would have expected is you have the 92 at the beginning, then you have half of it, and then you have 0. Okay, but now we have 73 different parts, and that makes no sense at all. let's see why this is. So disconnected, get all connected nodes. I would assume that this is the problem. So let's look into it. Run this again. Now the element is arbitrary, right? So this should be something which is not really bothering us. It has a property ID. It has 4 nodes. That's all good. Now we look into this connected nodes. So this is wrong, but I have to do that. So get connected elements. I will also look into this. So if the length is 0, then I append the self. That makes sense for me. Then I have the length before is 1. Then we have something which is doing stuff here. Then we have the length after, which is 2000. That's a lot of new. It's a lot of new. That's a lot of new elements. I would not think, or I would have not thought that it would be that many, because you have for every element in connected element, which is 1, then you have for every neighbor in element neighbors, those are like 4 or 8 or something like that. And if the neighbor is not there, then connected elements append neighbor. So the continue may be also included somehow the thing here. But the length before, what's the length before is 1, and then the length after, what's the length after? It's a lot, 2221. So it's not the same, so it will get, yeah, and then we have the connected elements. But is this now working? Or is this messing it up? No, this is not messing it up. So we have that, so we will step over it. We have the length before, then we can continue. What's the length after? 2221, which seems to be the same as before. So 17366 is the element which was there, but doesn't make any difference. Can search for the element here. We have now 2 elements. This is the one we had before, so I think we can leave that. Yeah, so this would be something. So maybe the neighbor calculation is still something which is not working. Maybe that's the thing. Let's up that to 50, but I'm not sure if that's really making it any different. I don't think so, to be honest. No, I don't think so. But you see, I have to debug here. And I unfortunately cannot make that today to a complete state, I think. What would be a simple thing here? Yeah, I can do something. We can make something like a print statement here. Something like this. And then let's maybe run that again and see what cluster we get. The starting element would also be nice, but I missed that opportunity. So this is what we have here. And I will copy that. So those are those 2000 values. Copy that and now paste that in here. Elements by ID. So that's that. So somehow it worked until it didn't. That's strange. So it worked. Maybe it worked going from one of the nodes here and then traveling here. So there's a state. Yeah. Okay. I think I have an idea what it could be. Let's go to the playground. Let's go to the neighbor calculation. So this seems to be problematic. If we would wanted to do a little bit more of that, we could do. But to be honest, I'm not really sure if it's the neighbor. I'm not sure if it's the neighbor. It could also be that the growing method didn't work. But how on earth could that be? How on earth could that be? Let's check that. So the get all connected nodes. So the problem is in the get all connected elements. Now you have a list and you loop through that list and then you loop through every neighbor, and if the neighbor is not in the connected elements, then you add it. So basically it is a neighbor problem. Because how could it be that you don't add new elements to it if you have neighbors which are not in there, right? Right. So I think this should be a neighbor problem. But if it's a neighbor problem, then I would assume that we have to make this reverse thing. If the element not in potential neighbor neighbors, if the potential neighbor not in element neighbors, and I think this is even the more important one. But to be honest, let's try it. Because I'm not sure so much about. Oh, I should maybe clear the console here. What am I doing here? Why am I here? Ah, yeah, okay. Still the same problem. Still the same problem. It's interesting, right? Maybe the centroid calculation is also wrong. Something with yeah, I'm not sure about this. Strange that it has. Strange that the trias are missing. Why are the trias missing? So okay, basically what I have to do is to check if the neighbors are correct. I can check that by going to an element ID, for example, this one, and see why the hell does it not pick up those neighbors? Because it obviously didn't. So the 16193, um, the neighbors of this element would be interesting. Um, yeah, and then see about why this is the case. So to look into the neighbor calculation here and why it did not pick it up. But I think I cannot do that today. So I should be in bed and yeah. So the test will fail. The linting will fail. That's all in the bin for today. So we really cannot commit something today. Um, but maybe we will just do the linting and call it a day. So neighbors output folder is not used. Okay, let's comment that. That's okay. Then here, nodes IDs. That should be node IDs. Yeah, maybe sometimes the linter gets you where you need to go. Was it the only one? Yeah. Where did that happen? Yeah, here. So if I have a second line, I would not have picked it up, right? So that could, for example, basically be it, right? That's why linting is so important. And yeah, you see a real life example there. Cannot guarantee that it is the case. Here there's an import error. Why the hell should there be an input error? Yeah, I think that's because the task install has to be done to update the latest things. And then dangerous default value empty list as argument. Yeah, okay. And then we have something unnecessary. So we can do that like this. And here we should not do something like this. So that means that get all connected elements should be done here with an empty list. Or maybe with the self. That's also good. Okay, oh, not task install again, but task lint. That would be a great thing if this was the issue and we would now have solved it with the linting. That would be a really great thing. So it does not do that. Poetry update. Then we have some missing docstring. Yeah, let's skip that to do because I think the linting will complain about this too. Okay, so linting is good. Now I want to see if it's working. Come on, that has to be the key. I mean, if I did not put the node IDs in it, the neighbors will be wrong. And that would be so easy. But it's not the case. Yeah, it's not the case. Yeah, I will just let it run through and have that awful output at the end and then call it a day, I think. But I think the way forward would be clear. We have to check the neighbors and we have to check why this is not working. There's also a lot of duplicates, right? I'm not sure why this is doing the duplicate thing so much. Yeah, okay, but it's better. To be honest, it's a lot better. So we now have 15 parts and 15 separate forces, and yeah, I think we're not too far away from completing this. But there's a bug, I cannot solve it today. But I will tomorrow. So thank you everybody for being here. So I have a chat here. I just got here, but it seems like you're dealing with something complicated. I will watch the whole stream later. Good luck. Yeah, it's the end of the stream, to be honest. The thing is, maybe I'll do a short recap that saves you the time of having to watch the whole stream, and also it gives me the opportunity to put a timestamp where the recap is what we did today. So basically, what we did today is we started again with this model. And basically, what we wanted to do is to make the differentiation between the parts automatic, so that you don't have to use different properties, because that was the easy solution. But that with by attached more or less functionality, you would see which parts are connected together. So those could have the same property then. For this, we would have to have neighbor relationships. That means we want to have the information. This element is connected to what other elements. And I think that's the juicy part of this stream, how to do this with a KD tree. Because that's really a thing which otherwise you cannot solve this in time. For simple models, yes, but you don't do loops with for every element, for every other element. If I share a node, I'm a neighbor. This is really bad design. So k-dimensional tree is the solution for that, and to do this efficiently. Now, somewhere this is bugged, but we will see about this tomorrow. Um, Basically, what we accomplished is having the neighbor information in every element, having the node to element relationship in every node, and we also have a method which can grow from starting from one element to have every element which is connected. So those would be all the blue elements. Basically, we did all that, but it's not working. So it means that it stops adding new elements, and it's not getting all the blue data here. And yeah, that's a shame. But I think sometimes you have to know when to let go and come back on the next day with a fresh mind. And I think for today, I think this is exactly what it is. All right. So thanks again for being here, for contributing. If there's anything I could do or cover in the future which interests you, if you would have a tool proposal or something like that, just shoot me a message. And I will happily look if I have the time and resources to do this. And yeah, so thanks for watching, and see you later, guys. Have a good night, day, whatever it is for you. Bye, guys.